Okay, all right. So we have our data set 2. So data set 2 is okay, is the one that I've already done some manipulations on. So you can see this section C. Yesterday we were trying to talk about how we wanted to do a knowledge, attitude, and practice analysis, whereby we will be able to add up all the sections, we'll be able to add it up based on the score, we received. So based on the score we have received from the client, so we want to actually have a sum. So we plan to have a sum of the analysis. Sorry, we plan to have a sum of the section. So let me just see. So so let me quickly review with you we got to this point, how we got to these numbers. Remember, from the original data set, it wasn't like that. It was yes, no, and I don't know that we had in that section. So this is the original data set, original section. So we have yes, no, no, yes, no. So remember yesterday that I tried to show us how to convert these responses into an actual score by going into your your edit menu. So from your edit menu, what you are looking for is you are looking for replace. So that is in a bid to replace yes with one, so that you want to now tell the software to change yes to a score of one. So under this variable, so you would you select variable, select the one of interest, select it. So once you unselect it, once that is done, you click on replace all. So automatically it's going to replace all the yeses with one. Do that for the next one. Just select it. Once you click on the variable here, you see the column is going to change. Click on replace all. So you do that for all of them. And also you also have to be mindful of the ones that have negative scores. Remember yesterday I showed you from the client scoring document. So from the client scoring document, we have so the client already gave us she already gave us how to score. She gave us a hint on how to score it. That's what we are going to use. So eventually, by the time you do the scoring and all those things, you'll be left with. So this is where the scoring document is. Let's have this now. So this is scoring. So the answer should be mindful of the one that has of the questions that have negative marking or negative scoring rather. Do all hepatitis B infected people present with signs and symptoms? So the correct answer here is yes. Is no. Sorry, is no. So that's what is going to be scored one. All right, so that's what you just do. That's what you do for everything. You replace yes with one, and others will be zero. So and I went ahead to now show us what I did with other ones. So since I've done since I've replaced the yeses with one, how about the remaining responses there? So I said what I usually do is I usually sort. I sort ascendingly. So that will allow me to have you sort ascendingly. So you have number first, and then you have your alphabet. That's you have your no, I don't know, like that. No, I don't know. So I said I would change the first one, the first no to zero. I'll just type in zero there. Then I will copy it. Copy is you right click, it brings out these options. So you click on copy. So when I click on copy, I would highlight everything. I will highlight the rest. So when that is done, I'm going to right click again and use paste. So paste is going to convert everything to zero. So I'll do the same thing for the next one. Sort ascendingly. You sort so it automatically rearranges it this way. So every other response is zero, right? So we do the same thing. Type in our zero, we copy, we mark, we select, highlight, you know, select the other ones. And once that is done, you paste your zero. So eventually, what you have is a table like this. So this is data set two. So what you have is a table like this. So now I was trying to show us yesterday how to how to go about the summation. So we want to sum up the whole section A so that we'll be able to have particular score for each of the participants, which you now change it to percentage and we'll be able to grade it. Remember yesterday I said the client told me that she wanted me to grade it. Anybody that has a score of 70% and above will be given will be said to have a good knowledge. Anyone that scores below 70, 69 downward will be said to have poor knowledge. So that's what we're going to do now. So let's go to our menu. So we'll go to transform, we'll go to compute variable. So compute variable is where we write some command. So let's our new variable that will bear the score. Let's call it knowledge score. That's the new variable. So now what we want to do is now I want to write an expression uh, where we're going to add up. We're going to add up all the variables. We add them up. So we add them up. So starting from, have you heard about hepatitis B? So starting from there, we'll add it up. Add it up. Click on plus. Add it to the next one. Click on plus. Add it to the next one. Click on plus. Add it to the next one. So you keep doing that. Keep doing that until you finish that section on knowledge. Remember, section C is on knowledge. So do that for everything. So keep doing that. So I hope we are following along. I hope we are using our laptops to follow along. Very important. Yes, so that's everything. So we'll close our bracket. Yes. So we've done the addition now. So what we want to do is now we want to actually write a mathematical expression such that we're going to add up everything, and everything will now be multiplied. Everything now be converted into percentage. So that's what we want to do. So we add up. So we've already written the expression to add up all the variables now. So now what we want to do is now continue the expression to so that we'll be able to have everything in percentage. So from the questionnaire, there are 19 variables. Let's confirm it. There are 19. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So is there a cure for chronic hepatitis B? That's the last one. So there are 19 variables. So that means we are adding everything 19, right? And I want to convert it to percentage. So what we'll do is that we'll just multiply this expression. Multiply it by what? Multiply it by 100 over 19. That's that's what will give us our percentage, because everything is 19. All the variables here are 19. So for us to add everything up and convert it to percentage, to convert it to 100%, we need to actually do we need to multiply it by 100 and divide by 19. So we need to write a formula again. Times bracket 100 divided by 19. So if all the variables you're working with, if they are 10, you're going to multiply by 100 divided by 10. If they are 5, multiply by 100 divided by. So essentially, the denominator here must correspond to the total number of all the variables for you to work up your expression to percentage. So that's what we have done now. So let's see if we'll be able to let's see if it will make sense. So we've written the expression now. So let's continue. We click on OK. All right. So remember I said any new variable that you get will come out last. So this is it. Can you see that it is bearing the name knowledge score? So these are the percentage. So this is percentage. So this is percentage. All right. So let me see if I can get the highest this thing here. I can quickly do a quick descriptive to know the highest and the lowest. Okay, so from doing a quick descriptive, the highest score is what? 84.221, while the lowest one is 21.5. All right, so 21.5. Okay, so what's the next thing to do now? So the next thing to do is to use our record variable our recode into different variable to now to instruct the software that any anybody that scores between 70 and 100 should be given good knowledge and should be rated good knowledge. So this is what we do. So we go to recode, we go to transform, we go to recode into different variable. Click on that. So we are interested in working with knowledge score. So drag it here. So so output variable. So what name should we give new the new variable? Let's just say knowledge. Let's say overall knowledge. Overall knowledge. Right? Click on change. So let's go and set the range. So first thing we'll do is go to this range, select it. So let's say 70 through 100. Right? Click on your output variable as string. Click on it. So go to your values. So give it good. So that means anyone that has 70 to 100 will be scored good. You add it. Can you see it? 70 through 100 is good knowledge. So meanwhile for the remaining ones, that's 69 downwards, Abby. You go to remember we did this with our with our age the first time we met. So go to range lowest true value. So lowest true 69 downwards. So that's that. So we'll call it 4. Add it. Click on continue. Click on OK. So just close this one. Okay. So do you see that instantly the overall knowledge came out, and we have so automatically now it has already given them their scores. So 57.89 is poor. So is there anybody that has good knowledge here? Or do they all have poor knowledge? Okay, all right. So one more thing. So for us to quickly know how many people have good knowledge and poor knowledge, by now you should know that we'll quickly run a descriptive statistics. Just click on the heading here, right click on descriptive statistics. Can you see it? Can you see it? So based on the range that the clients gave me, 70 to 100, we're able to deduce that 5 people out of 180 participants had good knowledge, which amounts to 2.8%. Do you see that? You see that? So that's it's a very interesting it's a very interesting thing we've done. So I will give you the section D as assignment. So section D, you do the other one. You do it the same way. So essentially, we've done the knowledge. So we've arrived at 2.8. 2.8 people have 2.8 people had good knowledge in this study, while 97.2 had poor knowledge. So the remaining one, section D, practice, practice. So you will do it. You do it and also let me know. So you do it and send to my mail. So this one is quite easy. So you just follow through what I did. Okay, so right now, is there any question? Do you have any questions? You have done. If you have questions, you can raise up your hand. Okay.
The
All right.
uh, I don't have a question. Oh. I just feel like the process is simple enough that with practice and if someone can rewatch the video,
Yes,
someone will understand it.
that's very good of you, sir. That, that's very good. It's very simple enough. Just straightforward.
Yes, sir.
Straightforward. Okay, no problem. So today, okay, we'll just quickly touch on we'll touch on visualization. So we want to visualize the data. To, to okay, so let me just share screen. So SPSS has a very easy way of creating beautiful charts. You know, they say a picture is worth more than 1,000 words. So that's very true for SPSS. A picture is worth more than 1,000 words. So now we want to visualize our data. So for us to do that, you see graphs here. Go to graphs. So you can see usually you have to use chart builder. Use chart builder. So chart builder allows you to build your own chart, your own graph from the scratch. So you can see these are your variables. These are the variables from which you want to draw your graphs. This is where the more like a preview. This is where the preview is going to be shown. The preview of your graph will be shown here. Then you can edit some properties. You can change appearance. You can do some things here. And these are basically the graphs to choose from. So we have favorites. They are not favorites for me yet. So you have bar charts. You can see the different bar charts, different types of bar charts. You have line graph, you have area graph, and the likes. All right. So let's dive in. So for bar chart, bar chart is usually used for categorical data. That's for qualitative data like age group, gender, marital status, and the likes. So bar chart is going to plot a graph of the category on your x-axis. X-axis is the vertical line. So it's going to plot the categories. That is, for example, in gender, female and male will be plotted on x-axis against their frequency on the y-axis. So the y-axis is the vertical line. So you see the frequency, it will be graduated from 0, 5, 20 like that to 100. Depending on the frequency on the vertical axis, y-axis against x-axis. So let's just do that. So let's draw a simple bar chart. So go to bar. You double click on it and drag it and drop it here. So once that is done, let's use age group. Drop your age group. You double click the variable which is age group. You drag it to your axis. Drag it there. That's all. That's all. So by the time you click on OK, so it's going to show on your. Why is it not showing? Okay, it's processing. Yes, it's out. So it will show on your output page. This is your rough page, your rough sheet. So let's try some more. So you can explore. You can explore. Like, you know, I would like you to actually explore. You can, of course, this there's a cluster bar here. No, cluster bar is used for two categories. Like is used for maybe two categorical data. So when you have two categorical data to deal with, you can use clustered. You can use clustered cluster. I'm coming. Sorry. Okay. I'm coming. I'm checking something out. Okay. So, mm, okay. So what I did was that. So what I did was that I was trying to see. I wanted to I wanted to do a cluster bar chart of age group and gender. So I want to see in each gender, or in each gender, what is the age group in each gender. Do you get what I mean? Like it's going to in female gender.
Now
The
compare
female,
the data.
yes, you compare the group. So you put the first variable in x-axis, then the second variable gender, you put it on cluster on, you put it here. So we click on OK. So it generates. So you see what we have here now. So female,
Hmm.
female is the blue bar, while male is the red bar. So that's just that. So you can explore more, and explore more. So it's very easy. So line graph is usually used for I think, yeah, qualitative data. I mean, sorry, quantitative data. Sorry. So line graph. Let's say, for example, let's use our mm, let's use age age, right? Okay, so let's use age, and let's see the results. So you can see the line graph of age. You can see the highs and low. So basically, that's line graph for you. So line graph is used for quantitative data. That's numbers. So for example, maybe the variable can be sales, sales, you know, sales and maybe sales over the months. So in that regard, put you can put the sales over the month, put sales on the x axis and put the months like January, February, like the date, put it on y axis here. So it's going to plot the graph like that for you. So area is basically more like a line graph. So area is just that area will have more to have more robust and have more robust. So area is also used for quantitative data. Area graph. Can you see? Area is just the same thing. Just that the boundaries. I mean, there are boundaries. They are well defined boundaries. You see it. So that's a boundary. Everything is the graph is enclosed in area chart. Meanwhile, in line chart, it's not enclosed. It's not enclosed. So just go through this thing, explore. So pie charts. We are all familiar with pie chart. So pie chart is used for qualitative data. Let's for example, let's do educational level. So slice by this slice by is what so we'll say we want to slice it by the educational level. So let's put it here. So that's all. Click on it. Click on your OK. So this is how it is. So then something I didn't okay, let me just so you can actually edit these charts. These are charts. You can edit them to our own preference. Let me just edit. Let me see if I can edit some things about this pie chart. How to do that is you double click on this space. So once you double click, it brings out the editor. Can you see this? Can you see chart editor? So if you want to do
Yeah.
some things with the color, if you want to change the color, you want to do some things, you can just easily do that.
The chart editor.
You want to bring out something, you want to pull out one of the sections, you click on it. So it's just for you to explore. Even myself, I still get to explore some things that I learn day by day. So just you know, you can change color. You can change the color. You double click on the. Let's say you want to change this orange to maybe purple now. You change it to purple. Click your purple. Apply. Close. Ah, it did not change. What happened? Okay. So you want to change it to purple. Fill. Okay. All right. Fill. Let's fill it in. It's purple. Ah, it's not changing. Okay, don't worry. Just I don't know why it's not changing, but it's meant to change. It's supposed to change. Just check. Anyways, okay. Anyways, so that's just that. So it's meant to change. So, like I said, just explore, explore. All right. So let's check some other charts. Some other charts that are there. So scatter plot. Scatter plot is also used for quantitative data. Scatter plot. That's scatter. So sometimes if you want to, if you are dealing with two quantitative data that is maybe you want to check for maybe if there's any correlation between two quantitative data. Scatter plots can be so useful. So these are examples of scatter plot. This is simple scatter plot. So quantitative, let's put our age. Our age there. Filter. That's filter. Mm, filter. Age. That's mention. Okay. So that's scatter plot. So if you want
Mm.
to,
Use this one in football analysis sometimes. I used to see this kind of scattered plots.
okay, yes. Full analysis. Okay, you're right, yeah, you're right. All right.
Time I've seen it used.
So you can explore other ones, other type of scatter plot. Histogram, right? You talked about histogram yesterday. Histogram is used for what's it called? It's used for quantitative data. So let's have it. So this is the histogram. So that's I mean those are the ones that you have to deal with. The box plot. Box plot is also very interesting. Box plot is also used for quantitative data. So box plot will give you the median, the interquartile Q2, interquartile Q3 to give you the outliers, and so it's also very interesting. So this box plot. So box plot essentially is going to show you central tendency. It will show you a central tendency. So it's just for you to actually know how to interpret it. We need to know how to interpret it. So I think that's that about SPSS visualization. Then there's dual axis. That's if you are dealing with you're dealing with two variables. Two variables. You want to have maybe age and something. So maybe age will be plotted in a line graph against bar charts of gender. So something like that. So let's try it. So now we are trying to do age. So we're trying to do age against gender. So gender will be plotted on a bar chart, and age will be plotted on line graph. So let's see what we come up with. Okay, I don't know. Okay, this is mean age. Sorry, mean age. Mm. Let me see. Okay, mean age. Let me see if I can use ordinary age. Let's hope it works. It's not going to work. It's not going to work. Okay, so I think basically this works for mean age and what's it called, and categorical data. So from here you can tell that the mean here, the mean will probably, so the mean age here is 35 for the mean age is 30 for female, while the mean age is 35 for male. So I think that's just that. Okay, all right. So let's move on. Let's move on. Let's move on. Okay, so right about now we are going to be looking at inferential statistics. Inferential statistics. So that's where you need to know some things about p-value, normal distribution, and the likes. So let me just try to just explain p-value and the concept of p-value in a layman's language. So p-value basically is a scientific approach to certifying a statistical test. How do I mean? I say scientific approach because it has to do with probability. So p-value, the meaning of p-value is probability value. Essentially, it means that at what probability is this your particular test, particular statistical test or hypothesis, at what probability is it correct? So scientifically, for most science for most science studies, most science research, they've agreed that the any statistical test that is less than, that is higher than 95% probable is significant. So I don't know if you have heard of something like this test is statistically significant. This particular test is not statistically significant. So what comes into play there is just the concept of p-value. So it's agreed that p-value of 0.05 0.05 is the same as 5%. So 5% of an event not based on uncertainty. Okay, let me try to come again. So when you say p-value of 0.05, in probability, sometimes they use decimal, and sometimes they also use percentage. So in probability, a 100% probability is the same thing as 1.0. So in probability, you can't say someone can never be 101% sure. So the highest level of certainty, of assurance, of you being sure, of you being probable, is what is 100, and the lowest state of uncertainty, of not being sure, is 0%. So in essence, that's to tell you that no, so now mathematically that 100% is the same thing as one. You have 100% or one. So now when it comes to p-value for research or data analysis and or some data modeling, the consensus is to accept a p-value of 0.05 as a level of significance. Some call it alpha level, some call it significant level. So basically, in a layman's language, when you say p-value of 0.05, it means that the researcher the researcher can tell you that the level of this research not not happening by chance is 5%. That means that it's 5%. I mean, that means that the level of it happening scientifically, like it happening correctly, no mago, no gambling, is 95%. So it's like two sides of a coin, 5% and 95%. So when someone says the p-value is five is the p-value is 0.05, person is saying that the um the state of that thing, not of that particular test, not being sure. Like, okay, let's say now I'm have to do a research now between two groups of people. So these people, they have high blood pressure. So we want to now know we want to know if there's a difference between the two groups of people that have high blood pressure. Already we've gone to take the we've gone to the field. We've taken samples from the test group, who are the the known cases of people that have high blood pressure. And we've gone to field to also take samples from people who do not have high blood pressure. So maybe we now administer a certain intervention. Maybe gave them we gave you know we gave the people that have high blood pressure, we gave them we administered a drug. We gave them drug for the high blood pressure. For the people that do not have the high blood pressure, we gave them placebo. We just give them maybe chalk or something. So they took it in. Now we came around again, we now took their blood pressure. So now we want to now test the effect of our intervention. That's our chalk and anti BP drug. So we want to test it. So we want to now say, okay, so after we now tested it, we want to now find the difference between the blood pressure of the people that have the test group and the control group. So maybe after doing the whole aggregate, the whole average and the mean and the whole statistics and everything, we have two answers. Now we now want to now know that statistically, see emphasis on statistically, because you have to be statistically correct. So we want to now emphasize that, okay, statistically, these two group of people, is there a real difference between their blood pressure after giving them the drugs and the placebo? So after we've done that, we use t-test, for example. So this test gave us a certain number, maybe 2 point something, 2.3 something something. Now we need something to actually seal, like a stamp on that t-test, that will say, okay, indeed, there's a difference between these two groups. And that thing is what we call p-value. So any p-value, if you are doing analysis for your test, any p-value of less than 0.05 is accepted as a level of significance. Do you get the point now? So, but I would like you to go and read more about it, because you have tried to explain it in layman language, but you need to actually read about it. Then also try to read about normal distribution. Normal distribution. So these are things I want us to read about tomorrow, so that we can actually push ahead tomorrow. We can do something tomorrow. By tomorrow we'll finish this training. We don't have much remaining again. Tomorrow we'll finish. So normal distribution. Let me just quickly rush over it. So when you say normal distribution is kind of a kind of let me see. Okay, for example, in this age group now, this age histogram, normal distribution is type of in a population of maybe population of people that are using for that are using for your research. the center, you see that most of the um how will I say, okay, let's say you are looking for age, you are trying to assess the age of a particular population. You notice that in a normal distribution, the the middle, you see that the middle will have more. The middle, the center of the histogram of the graph, of we have more of the ages there. How do I mean? The frequency of people, let's say this graph now, the x-axis started from 0, and it's up to about 80 abi. So in a normal distribution, most of the participants will be around 40, and gradually everything will now taper off. Just everything will just go down like that. So that's how to actually see normal distribution. And another thing about normal distribution is that in normal distribution, the mean and the median, they are almost the mean and the median, they are almost the same. They are almost the same. Sometimes they may even be the same thing. Sometimes they'll be close. So I would like you to go and read more about normal distribution. Um, so yes, just go and read about it. Let me see if I can pull up the the normal curve of this one. Okay, so we have normal curve. So this is normal curve of this age group, of this histogram. By the time you look at the top of the curve, and you just you draw draw an imaginary line down, it's going to correspond to your mean. Just draw an imaginary line down from this top down like this. It corresponds to your mean. So in a normal distribution, the mean should be almost the same thing as the median. So these are things that you get to understand by the time you read more. So then that also leads us to normality test. So normality test is a test used to know if your quantitative data, if they are in the normal distribution. For example, like this age now, let's see if our age is actually a normal distribution. So to do that, to do normality test. So right now I'm teaching us how to do normality test now. So I I know it's quite a lot to actually take in and solve at once, but it's it's doable. It's doable. You can do it. You can actually understand everything. In fact, within 5 days, you can understand everything. And God so good, we have access to video recording. So at the same time, you also need to read. You need to just read and study, because this is just more like a crash course for us. So we need to actually go back home and do our own assignment. So let's see normality test. Let's see if our age, if it's normal, if it's normally distributed. So we go to analyze, go to descriptive statistics, go to explore, go to explore. So age abi, so put the age in dependent list, put it there. So let's see what we can do here. Statistics, just leave it at default. Plot. So we need to let's choose histogram. Let's leave this term and leave. Click on this histogram. So click on. So now let's check normality plot. So this is very important. You check it. Continue. So click on OK. Okay, so it's coming out now. It's processing. It's processing. Okay, so these are descriptive of age. This is the test of normality. So there are two tests. There's a there's Kolmogorov-Smirnov test and there's a Shapiro-Wilk test. So these are the two tests that they use in statistical data analysis, even in some machine learning, deep learning, they use some of this. They use the Shapiro-Wilk test to know if your test is normal. So so uh, if you want to know if your data, if your quantitative data, if it's a normally distributed data, look at the test here, 0.158. Okay, that's not even the issue. The issue now is this SIG. When you see SIG in SPSS, that's p-value. SIG in SPSS most times is p-value. Is no, normal every time is p-value. That's your significance level. Now for normality test, if you can write this down, I would like you to write it down because this is an exception to the p-value rule. I think this is only exception to the p-value rule. I said for p-value, I said for a test to be significant, it has to be what, less than 0.05. But for normality test, I think that's the only known exception that I know yet. I don't know if there are other ones. Reverse is the case. For normality test, if the p-value is less than 0.05, hmm, if it's less than 0.05, that test is not normal. I mean the what's it called, the data, in this case age group, in this case age, the age is not normally distributed. But if it's more than 0.05, like maybe 0.06, 0.07, it is what? It is normally distributed. So you see that it's actually it's actually reverse of the normal p-value rule. It's like going reverse. So let me see what we can do again. So I think from this, I think we're actually done with material A. So for this our inferential statistics, we will dwell more on material B. So up to this point, is there any question? Anything that you need to clarify? Okay.
Most of the information are still new to me, so
All right.
I
All right.
have
Don't
to.
worry.
I'm not
Yeah.
the kind of person that takes in information new ones like that. So I have to
Yeah.
go back, sit
It's
it,
okay.
and
It's
have
okay.
questions.
Yeah. Sorry. I understand. So in fact, I will send a small book to the page for us to
All
just
right.
read. Yes. Or you can even go on Google and read about, just read about
Sure.
these three things: normal distribution, p-value, and normality test. So those three things, if you can read about them, yeah, I mean, you are good to go. So
Okay, sir. Thank you.
okay, all right. So let's see. So I'm actually opening the material B. So I'm in material B and I open the data set one. So let me just give a brief overview of this material B. So this material B is actually a test done for it's a research work for a condition. They call it pre-eclampsia. So pre-eclampsia is hypertension in pregnant women. So the researcher wanted to know if um if there's a significant difference in pregnant women who have been diagnosed of preeclampsia and the pregnant women who do not have that preeclampsia. Preeclampsia, I said, is hypertension in pregnancy. All right, so so the person went to the ward, maternity ward, and you know um gave them some questionnaires took their blood samples and their BP, that's SBP and DBP, that's systolic blood pressure and diastolic blood pressure. He took it and also, you know, divided them into two groups. The people that are known case of hypertension, the pregnant women that are known case of hypertension, and the pregnant women that are not hypertensive. So she took them. So this is more like a test and control study. So let me see. There you go. Um, okay, sorry. Let me look for one that is more. This one. So she has two category. Okay. So let's okay. Sorry, I'm using okay. I'm using data set 3 now. Data set 3. That's what I'm using now. Okay. Data set 3. So if you open it, you see that the first variable here is group. You have the group, you have some are control, some are test. Do you see that? Some are test, some are control. So this serial number, let me take it back to it should be first. So this is your age range. This is your age. So they have been grouped into age group, religion, education, ethnic group, marital status. This NP is number of previous pregnancy. NP delivery is number of previous delivery. NPMS, number of miscarriage or abortion, trimester, pre-eclampsia, systolic blood pressure, diastolic blood pressure, WBC. All right, so I want to just show us something on normality test. Normality test. So, like I said, if you want to know if your data is normally distributed, you go to what? Go to analyze, go to descriptive, go to explore. So let's just see. Let's let's check let's check for age range, um, systolic blood pressure, diastolic blood pressure. What else again? WBC. Let's put everything there. Let's check our. Let's leave it like that. Plot. Let's check our normality plus and histogram. And check stem and leaf. Continue. So let's wait while it's processing now. Okay, so it's done. So this is summary of what we just ran. This is summary. So this is the descriptive age. You can see the mean. Mean is 33.11. You can see everything. For the SPB 143, you can see it. So let's go to our statistics. Hmm. Okay. Okay. So based on the p-value SIG here 0.2000, only age range is normally distributed. Other ones are 0.5 to 0.15, which are C less than 0.05. So only age range is normally distributed. So this is the histogram for age. You can see everything. Everything is. You can see all the charts. Like they are tending towards the center. They are tending towards the center of the graph. So that's how you know. And you can see this arrow. Sorry, this line that passes across the age. So it's everything is is linear. Everything is linear. So it's showing a very good relationship the between the between the data points. So like that. So I think that's just that about normality test. So why do we even need this normality test? Why can't we just go ahead and do our statistics? The reason why we need normality test is, yeah, for inferential statistics, is because normality test, we need to know what we're dealing with. Are we dealing with a normal distributed data or some other form of data? Some other form of data. So if we know we are dealing with a normally distributed data, there are some tests that can be performed. There are some tests that can be performed. Like for example, if you are trying to establish the difference between the two groups, in this case the test and control group, we are going to use t-test to look for the difference between, let's say we want to know the difference between their blood pressure. That is there an actual difference between blood pressure? We can use t-test. So there are some tests that can be allowed on a normal distributed data. Once the data is not normal distributed, those tests will not be able to use them. We have to go and use there are some tests called non-parametric tests. So if your data set did not pass normality test, yeah, you can't use normal distributed test. You can't use all those t-test, ANOVA. I'm very sure you must have heard of t-test, ANOVA, correlation, maneuver. You can't use those ones. You have to go and look for another type of test used for them. So so today we're actually moving fast today. Oh. Yeah, because I know I'm actually, you know, releasing a lot of information, and it might be too much to process, but I'm sure if we go back to look at the videos, we would understand them. So the first inferential statistics I want us to look at is test of difference. Test of difference. So what is test of difference? You know, I don't know. Is there anybody that has any idea about test of difference? Mr. Glory, I don't know. Do you know what test of difference is?
No, no, not exactly, sir.
Okay, okay,
So,
okay. So test of difference is that is you trying to look for the difference between two group. Difference between two group. Okay.
like two age group or something.
Yes, like two age group. Okay, okay. Let me even use something that is more familiar. Let's say score. Let's say you want to know if there is an actual difference between the score of two class. Maybe there's an SS3 class now, A and B. They both sat for English test, and they all scored. All of them scored different marks in
Yeah.
SS3A. SS3B also scored different marks. So you now say, okay, you as a data analyst, come and see that which class is actually performing better than the other one. How will you do it? You can easily say, okay, you want to add up all the score, Abi, add up all the score in SS3A, right?
Yeah.
And you can say, okay, you want to add up all the score in SS3B, right? So let's say
Yes, sir.
yes, that can actually work. You can work. You can add up all the tests. Let's say after adding up all the scores in SS3A, you got um you got an average of 18 over 20 in this test.
In this, that's yeah,
That's good, right? And
yeah.
you now went to go and you now add up the score of SS3B,
Necessarily.
and maybe they gave you 15.2 over 20. Obviously, many looking at the score, you will say SS3A is scoring better. Abi? Oh, it's not left. Okay. So I was saying, so So merely looking at, okay, so you can say merely looking at the two score, 18 over 20 and 15.2 over 20, you want to say that SS3 is doing better. But in the real sense, that's not how it works in data analysis. Like how it works is that you actually use some statistical test of difference. So those tests of difference will be the one that will be the basis for which you will say that SS3A that has scored 18 is actually doing better than SS3B that has scored 15.2. So um, one of such tests is T test. T test. T for tiger. So T test. So
Mm,
so that test will tell you that there's an actual difference. So what the test does is that the test is going to look for mean. Mean is just like an average. Mean is just like average. So it does the mean, calculate the standard deviation based on some other parameters, and it tells you that there is an actual difference between SS3A and SS3B. So it will now give you an extra seal, an extra stamp, which is your p-value. So by the time your p-value comes in, your p-value is giving it a stamp that bam, SS3A is truly doing better than SS3B. So do you see the idea? So that's the idea
yeah.
of t-test. So in data analysis, you don't just take things you don't just take things as they appear obviously. Okay, obviously 18 is higher than 15.2. Of course, you can be forced to say that 18, the score of SS3 is more than um, the score of SS3B. But that's not how it works in data analysis and statistics. There a must be a scientific basis for you to say that 18 is more than 15.2, which is where your t-test and p-value comes in. So now let's even now imagine that there are more than two classes. Let's say you have SS3A, SS3B, SS3C, SS3D. So that they become four now, right? There are four classes now. T-test will no longer work because t-test is only limited to two groups. T-test would work for SS3A and SS3B. Once it's more than two classes or two categories like that, two things, you start to talk about ANOVA. ANOVA is what? ANOVA is ANOVA. ANOVA is an acronym for analysis AN of O variance VA. ANOVA. Analysis AN of, that's your O, variance VA. So ANOVA will be able to check for the statistical difference between two or more groups, which t-test cannot do. Do you get the idea? So those are the common tests of difference that, that are there. So let me see if I can. Okay, sorry. I think I'm back now. Okay, so I said ANOVA will check for statistical difference between two or more groups, two, three, four, like that above. Even if there are 20 groups, ANOVA will do that for you. So that's the good thing about ANOVA. So let me just um let me just quickly show us how to do ANOVA and t-test. So after that, we would call it a day because I feel like you have said plenty things today, plenty things. Uh, it will take a while to sink in, but we can do it. So ANOVA now, sorry, t-test right now. So t-test. So remember I said this is our data set. The group, we have control group and test group. So you have see all the test group, see all the control participant. All right. So let's see. Let's play around. So let's see if there is this SBP. I said this SBP is what is systolic blood pressure. Is systolic
Okay.
blood pressure. That's after you
Let's
measure
do
your
it.
you use your BP. This DBP
Yeah.
is diastolic blood pressure. So let's see. You know, I said this data set is on pregnant women that have high blood pressure. Abi. So
Yeah.
let's see if the between the test and control group, if there is really any difference between their blood pressure. So from there, we will now know which group has the higher blood pressure. So how do you do that? We need to check for test of difference. We need to look for the difference between them. That's the basic thing. So let's go to analyze. So we want to do what? We want to do t-test because we are dealing with two groups. We want to do t-test. So there are many t-tests here, but the one that we will use for this particular test is independent samples t-test, the third one. So the test variable at the that's the that's the quantitative data that I want to compare. That's the quantitative, the blood group. Let's put SBP. Grouping variable. That's what we want to use to group. In this case, it's our test and control. Just imagine that the thing I talked about class in a class group before. In that setting now,
Yeah.
this test variable will be the score, will be the English score. The grouping variable will be the class. That's the SS3A, SS3B. So, but in our data set, we are doing something more scientific, something more scientific. So after you put your testing variable here and you put your grouping variable here, you go ahead and define group. Group one, just type one. Group two, just type two. Click on continue. Option, leave everything at default. Leave your bootstrap. Click on OK. So okay. So you can see t-test, you can see the group statistics, you can see it. So this is just yes. So look at the group now. We have test. The test participant, their number is 50. The mean, the mean of their SBP is 157.40. The SD is 23.6. Standard error of mean 3.3. For control, there are 25 control participants here. The mean is 114. So even merely looking at this mean, you can see that I mean, there's a remarkable difference. There's a huge difference, huge gap between the two of them. Look at, mean. I said mean is a statistical average. Mean average is a layman's word, but in data analysis and statistics, we refer to mean. Mean is more scientific. Mean is more scientific. So mean is like average in the normal context. So you can see that the average of their blood pressure is for control is lower than test. Even look at the standard deviation, it's lower than this thing. So of course you would expect that there should be some form of difference, some form of scientific statistical difference. So this table you don't really need much here. What you just target is you target your T and your SIG. So the T test is 8.672, while the SIG, I said SIG is significance level, that's p value, is 0.0000. So this is telling you that the mean difference is when you subtract this bigger mean minus this small mean, it gave 43.16. So it's telling you that this mean difference, this 43.1160, at the p-value of 0.0000 is what? Is statistically significant. That means that there is indeed that means that indeed the the test group have higher, they have higher blood pressure than the control group. Looking at the difference between the two of them, do you see that? So the difference is glaring. So the difference is glaring. Do you see that? So we need to, so you can play around, you can do some other things, you can check some for some other parameters. It's still the same method. Compare means, independent, let's this time around, let's change, let's use DPB. Define group one. Okay, continue. Okay, see. So even the DPB, diastolic blood pressure, is also still high for the test group. 26, the mean difference is 26.08 at p-value of 0.0000. You see, p-value. So this is p-value. So it's highly significant. It's highly significant. So you can still play around, check for some other things. Let's check for, what can we check for again? Okay, let's check for hemoglobin concentration, HB conc. Let's put it here. Let's see if there's any difference between their hemoglobin level. So can you see now? Can you see that the mean of the test group is 10.54, of the hemoglobin? The mean of the control group is 10.687. So there's really no difference. There's really no difference. No, really, no difference. So let's see our statistics. T-test is minus 0.358. P-value, you see p-value is 0.721. Remember I said p-value, for a p-value test to be significant, it has to be less than 0.05. So if it's higher than 0.05, it means that there's no significant difference. So now this these two mean now, there's no significant difference between them. It's just maybe just some arithmetic, mathematical difference, but scientifically, data analytically, whatever any form of, science this thing, it's not significant. It's not There's no difference between them. So now you've seen the use of t-test. So let's use ANOVA. Remember I said ANOVA deals with what? Deals with three, three group above. So, but at this point, I just want to see our screen to see if we are also following through, because we promised to use our laptops today. Even if
I I was using my system before, but that time when you were discussing this there was one operation we did before we started the statistics.
Okay,
So I went to open the SPSS so I can join. By the time I came back, I missed the entire. So I just had to. That's why. That's why I said to just focus on the exercise instead of
okay,
following with app.
okay,
uh
it's okay.
Otherwise, I
Um,
can
but you're
easily
really
snap
following.
the data.
Okay.
So that's why I did not bother trying to follow again because you are already used to the system and I'm just trying to find my way around.
Yeah, it's okay. It's okay. So, any other person, Mr. Fawaz, can you share your screen? Oh, Mr. Glory. Nice one. Nice one. Well done, Chief.
Yes, sir.
Yes, I'm trying to locate where I can share the screen now.
Okay. So,
Yes, sir.
yesterday, most people did not use their laptop yesterday. So, but I think today the effort is a bit much better. So, let me just quickly touch on ANOVA. So, ANOVA, we are using three groups. So, something might interest you. You might feel like you want to just see if there's any difference in the trimester. There are three trimester: first, second, third trimester. You want to see if if there's any if trimester, if maybe does blood pressure, does it increase with trimester, or you just want to find out something. So let's in that case, because trimester is there are three trimesters, so we can't use t test, we have to use ANOVA, right? So let's go to analyze, go to compare means, go to one way ANOVA. So one way ANOVA. So our dependent list is the quantitative data. That's numeric data. So let's bring in our SBP, uh, blood pressure. Okay, we can even bring in two. Let's just bring the two reading, the two blood pressure. All right. So our factor will be what? Our factor will be the determining group. That's the trimester. So we want to see what's happening in the trimester. Is there any difference? So contrast. Don't need to do anything here. Post hoc. Okay. Okay, don't worry. Post hoc, we'll talk about post hoc later. Mm. Post hoc is a Latin word for post hoc, is a Latin word for after this. After this. There's something called there's one Latin phrase, post hoc ergo propter hoc. That's after this, because of this. It's a Latin word. So basically, what post hoc does is that post hoc is like after the ANOVA analysis, it will further probe into the ANOVA to see which of the three groups are interacting more. But we don't let's not bother ourselves with all those things. So your options, you want to see your discrete statistics, you want to see it. Let's just check it. Continue. So click on okay. So all right. So this is your discrete statistics. So it describes it. You are seeing your okay. You are seeing your mean. You are seeing your okay. So in the category you have first trimester, second trimester, third trimester, and control. I think the control group here, they are people who are not pregnant. So you actually have four groups here: first trimester group, second trimester group, third trimester group, and control group. That's people that are not pregnant. So you can see their mean. You can see the mean SBP, the mean systolic blood pressure. You can see it. The same thing for diastolic blood pressure. You can see it. You can see the standard deviation. You can see the standard error. You can see lower boundary. You can see. So that's why I said we should check our descriptive. We should tick it. So ANOVA table itself now. So this F statistics, this F is the ANOVA test. This F is the ANOVA test. P value is 0.00000. So basically, it's telling you that there's a very strong difference in this um, research. So that means that it's telling you that trimester has to do with like trimester has an effect on blood pressure. And how do you now explain that? Like how do you now further probe into that? Just look at your descriptive. You see that first trimester, the average is 120. Second trimester is 150, what? 159. That means it's getting higher, abi? Third trimester at 158 is a bit almost the same thing as second trimester. Meanwhile, for control people that do not have pregnancy, is a 114, which is the lowest of all of the four groups. For the DPB, the diastolic blood pressure, fourth trimester 65, second trimester 101 and 102 sha. Third trimester approximately 100. For control is 73. So that's how you're able to explain it. So statistically and scientifically, there's a difference in blood pressure based on trimester. And according to trimester, there's a difference. So that's ANOVA for you. So ANOVA does the work of t-test, but it can do more than two groups. T-test we only compare two groups, while ANOVA compares more than two groups. We have three groups, four groups, four groups. Just have multiple things. So is there anything again that we can actually play around with here? Okay. Is there anything that has more than three groups? Okay. Okay, let's just play around with ethnic. How many ethnic group do you have here? Let me see. Maybe it's just two or three. Okay, okay, they are mostly Yoruba. Let's not play with that because that will be biased. If out of 75 people, 64 are Yoruba, what we'll get from our analysis will not be, it will be tilted. It will be let's look at age. Yes, age range, abi. Let's see. Can it work? Can it work? Can it work? Okay, let's see age range. So according to age range, it's not work. It's not work. You know why age range will not work? It's because age range, the variable setting, the type, it's a string data. It's a string variable. So string variable is not accepted in ANOVA. See the logo. See now, string. So it won't work. Let's look for okay, let's check marital status. How many people are married? Let's see. Okay, they're all married though. Ah, now we need a variable that has at least two groups here before we. Okay, let me check religion. There are only two religions. We are looking for three. Education status, abi? Let's check. Okay. Let's work with this. Let's work with this education status. Let's work with it. All right. So let's see what we can do. Analyze, compare means, ANOVA, education status. Okay. Okay. So you can see now. Look at the people. Look at the ANOVA test, F test, 1.2 for DPB is 1.005. Look at the this thing. Look at the p value. p-value SIG. P-value is what 0.331 and 0.335 for DPB. It's not significant. So of course you will not. Of course, there be any reason why educational level would have effect on blood pressure? Can there be any reason? Maybe maybe you can say due to education, maybe people might actually know how to check their blood pressure and all. But from this particular study, there's no effect of education on blood pressure because there's no difference. Okay, of course, look at the descriptive, look at the mean for primary. Under primary education is 166, abi. For secondary 143. But all of these difference are not really they're not really statistically significant. That's the point I'm trying to paint. That there can be mathematical difference, which is not how do I say it? Mathematical difference does not correspond to statistical difference. That's what I wanted you to to get from this our talk. There could be some obvious mathematical difference. Like you can see 166 is more than 143. 143 is more than 140, but that does not warrant that there will be some statistical difference. So all thanks to our p-value and the people that have come up with this model and all those things, and we actually so okay, so we can actually come up with something that is more concrete. So I think we've done a lot today. So tomorrow we'll still look at some other inferential statistics. Tomorrow we'll look at tests of association. We'll look at correlation and regression tomorrow. So tomorrow we are doing three things. We'll look at association, correlation, and regression. So and we'll call it a day. So but up to this point, is there any question? Are there questions? Ah, oh, okay, I'm offline. Oh, no, no, no. Sorry, it seems my computer went off. Sorry. My computer Wi-Fi went off. Let me connect again. Oh, okay. Sorry. No, okay, don't worry. I will just let me connect with my computer. I don't know why the Wi-Fi went off. Let me so this is my phone. I'm using my phone to actually speak now. Let me see if I can connect again. I think a normal call came in and the call disrupted my Wi-Fi. Okay, but anyways, I think let me just use my phone to talk about it. So what I'm just saying is that uh, on my screen, yeah, I was able to do the an over for educational status and blood pressure. So I was trying to see if there will be any form of difference between educational level, and there was no. I mean there were no difference, which might be expected. So, however, I noticed that in the primary people that have primary education, their blood pressure was 166. For people that have secondary education, their blood pressure was 143. People that have tertiary education, their own was 141. So I was now trying to say that because there's an apparent difference, apparent mathematical difference does not correct it does not always correspond to statistical difference. So it's what we confirm that is by the time we check our ANOVA test and the p-value. So from here now, the p-value is zero for systolic blood pressure. The p-value of the difference is 0.331. Meanwhile, for diastolic, the p-value is 0.3354. And if you remember, I said earlier that p-value for a test for a test to be considered statistically significant, the p-value must be less than 0.05. So now we are dealing with a p-value of 0.33 and 0.335. So it's of course not significant. So I use this example to show us that um an apparent mathematical difference is not equal to a statistical difference. That's what it means. So because we are seeing that primary education in their group, their blood pressure is high, and secondary education the other things that can also affect the overall statistics, like like your standard deviation. You have to consider that your standard error of mean, all of those things, they together they affect the overall statistics. So I think that's just what I'm trying to pass across. So I think from my end, I'm done. So tomorrow, I said tomorrow we'll look at for some other inferential statistics. You will look at tests of association. You will look at tests of correlation. You will look at tests of regression. So those are the three things we look at tomorrow. And by God's grace, tomorrow we would end the this thing. So I really commend our effort, as we are trying to follow through. I understand that this is more like a crash course, and for us to swallow this much information in a very short while, it's a lot, but it's something we can do. So to make it also easy for us, I'll send a book, a very short book, and the book is quite interesting. By the time you start reading it, you just see that it's interesting. So I'll send the book to the page, or maybe to our mail, so that we can read and just have the book is very interesting. It's going to break it down to an ordinary man's language. So I think from my end, I'm done with the teaching for today. Madam Olaide, Madam Ladi.